I'm Alex, and today I want to talk about our work on HECO, a fully homomorphic encryption compiler. This is joint work with my supervisor Anwar and my colleagues Patrick and Miro. And while I did this work during my PhD at ETH, I'm now at Interlab, so the usual disclaimers apply, and any opinions are my own. You know the drill. Back to the actual topic, what is FHE and why does it matter? I'm aware we just had another FHE talk, but for the sake of those who might be watching the recording or coming in later, I am going to recap this slightly. So existing techniques for securing data in transit and while at rest have seen really wide adoption, and they provide important protections, but those protections then need to be removed in order for the data to be processed. And by allowing data to stay encrypted also during computation, advanced crypto techniques such as MPC, ZKP, and of course FHE promise to significantly extend the range of applications for which true end-to-end security can be achieved. And while FHE is frequently still considered too impractical for applications, this is no longer true. And so over the last decade, for example, we've seen a several order of magnitude speed up, starting with the first implementations taking about 30 minutes to perform a single bit multiplication, to now being at a point where we can do this in a few tens of milliseconds. And beyond improvements to the underlying scheme, we've seen massive improvements on the algorithmic and application design, including better hardware utilization. So, from 2016, where the state of the art for an MNIST inference was a couple of minutes, we're now to hundreds of a second for the same task. And in fact, the community is now looking at more realistic problems like ImageNet, where a ResNet inference can be done in just a few seconds. And so thanks to the work of a variety of academic, industry, and both large and smaller startup work players, we are now working on making FHE even more efficient and expanding the range of possible applications. And as a result of that, we've already seen a first wave of high-profile real-world deployments. For example, the password monitoring service in Microsoft Edge, or the Korean COVID contact tracing application. And with performance no longer being the major constraint that it once was, we now have to ask ourselves, why isn't FHE being used more widely? Because these are basically the two applications I could find. And the reason is because developing and deploying FHE applications is notoriously hard. Both of these require teams of dedicated cryptographers and research engineers. And the reason why FHE is so hard is because, one, secure computation techniques inherently interleave tightly with the application logic. And so how you translate a function into a secure computation dramatically affects the performance and functionality you're going to get. FHE then also imposes a unique paradigm because it has limited expressiveness. Inherently, you just can't branch in a secure computation, and in practice, you're also limited to either binary or arithmetic circuits for the most part. And so you can't have things such as division or native comparison operations. Modern learning with error schemes also, modern FHE schemes are also based on learning with errors, which introduces noise that gets added up and needs to be managed very carefully using expensive ciphertext maintenance operations. And finally, many schemes introduce very expensive homomorphic operations, but then allow you to batch many thousands of values into a single ciphertext and to get a form of single instruction multiple data parallelism, but with very restricted data movement. Okay, so those are the challenges. Because of all of them, FHE tooling research has been happening for about as long as practical FHE research, starting all the way with the first implementations of practical FHE, focusing on just getting signal operations running. Then we very quickly got to the point of having FHE libraries where experienced developers can essentially assemble circuits at this level. But of course, they need to manually perform this noise management. And it wasn't until the 2019 EVA tool from Microsoft that we actually got tools that were able to abstract this and actually optimize this. And there's now been a series of work culminating in the one that we just saw before this that show how to do this even more optimally. However, these existing tools generally still assume that the input is this circuit level representation and don't consider the development process holistically. And so with HECO, we present the first fully end-to-end architecture for FHE development and show how our approach can help us to implement new, higher level optimizations that can give order of magnitude speedups compared to unoptimized code. And so in order to understand our proposed architecture, let's briefly consider what an FHE compiler used to look like, which was traditionally a thing that optimizes FHE circuits. But really, FHE applications span such a wide range of domains, and they each have their own paradigms and expressions. And when we lower these directly to circuits, we lose a large amount of information. And so we introduce a novel extension to the pipeline by introducing a high-level scheme-agnostic abstraction for FHE that allows us to implement higher-level optimizations as well. On the other hand, we want to move beyond just targeting software implementations and targeting underlying hardware directly, including upcoming dedicated hardware accelerators for FHE. Sorry, oh, that was loud. Cool, yeah, in order to do this, we need to move some of the underlying math into the compiler, which in turn then allows us to do new optimizations on the cryptographic level, or for example, scheduling in a hardware backend specific way. And in order to realize this stage architecture, in HECO, we rely on the MLIR compiler framework. In MLIR, you build intermediate representations from sets of operations. And so we introduce high-level scheme-agnostic operations for FHE and combine these with standard MLIR components, for example, for control flow, in order to get a high-level program representation. After optimization, these can then be lowered to the traditional FHE circuit representation, and from there, either target existing FHE implementations, such as the Microsoft C library, or via further low-level intermediate representations directly to the various hardware backends. In the following, I will focus on our high-level IR and the speedup we achieve by considering the translation to an FHE circuit more carefully. Specifically, we introduce an optimization that targets the SIMD-like parallelism, which is powerful but has really restricted data movement. You don't really get to permute or scatter gather, which are very common in other vectorized paradigms. Instead, all you get is this very limited cyclical rotation operation over ciphertexts. And so in order to show you why the existing vectorization techniques don't really transfer to the FHE setting, let's consider a simple image processing application. For this program, we iterate a 3x3 kernel over each pixel, and a natural approach here might be to unroll and try to vectorize the internal loops. However, because we need data movement to do this, rather than reducing the number of operations required, we actually introduce expensive homomorphic rotation operations. That means that our cost, in fact, goes up. In fact, it is possible to batch this program effectively, but it requires a significant different approach. So if we look at a few iterations of the program, specifically at what the underlying ciphertext look like and which slots are being touched by different iterations, we can see that we can't apply SIMD SIMD operations because the slots just don't align. And as data movement is so expensive, rotating to align these slots would result in the same high cost that we just saw earlier. And instead, we need to really change our perspective and focus on the operations for a single iteration. But keep in mind what's happening to the slots of the other iterations. Okay, for a single iteration, 9 pixels multiplied by a weight, right? And now, how do we select which one is which one? Well, we can sort of see that the relative offsets of the kernel pixels are similar across iterations. And if we select them just right, we end up with the pattern that we can then carefully rotate in a way that allows us to tackle not just one iteration, but in fact, all iterations at the same time. And that gives us an FHE program that doesn't require 9 times n squared rotations, but just 9 rotations. And that's assuming the ciphertext is large enough to hold the entire image. And obviously, this is just an example, and it relies really heavily on choosing the correct slot in each of the iterations. And in the paper, we generalize and automate this approach to apply similar batching techniques to a variety of different workloads. But because of time reasons, I'm going to have to refer you to the paper for this one. Instead, I'm just going to briefly show a few of our evaluation results, which demonstrate that HECO achieves an order of magnitude speedup compared to a baseline that doesn't consider batching. In fact, for larger problem sizes, HECO gives you more of a speedup, but we choose to report some of the smaller ones here because that allows us to compare to the optimal solutions generated by the synthesis-based Porcupine tool. So you can see that we've essentially matched the correct solution here, but we take seconds rather than the minutes or hours that synthesis-based approaches tend to take. So, in conclusion, with HECO, we presented the first end-to-end FAG toolchain architecture and demonstrated how this enables new optimizations that make efficient FAG accessible to non-experts. HECO is available as open source, and you can find the paper either on arXiv or, of course, on the USENIX website. And I want to thank all of the artifact evaluation reviewers for the lovely work they did in order to get us to those 3 lovely badges. In addition to the concrete HECO tool, I'm also currently leading a working group that incorporates all the major players in the FAG development space, and we're aiming to standardize a set of MLIR-based abstractions and interchange formats, based not just on HECO, but other MLIR-based follow-up work, in order to enable people to interoperate between different tool sets and choose, let's say, input languages, algorithmic optimizations, and hardware backends independently. Looking beyond this immediate thing, we can see that currently the landscape of FAG tools has successfully tackled a wide range of challenges, right? We just saw a talk about noise management. With HECO, we demonstrate how to tackle SIMD batching. And what we haven't really tackled as a community is the issue of limited expressiveness. We need to somehow find a way to enable developers to express just how their application should be translated to this more restrictive setting without needing to understand the cryptographic reasons for these restrictions in the first place. That's it for me. Thank you for your attention, and I'm happy to answer your question.